So last time we were talking about graphs, and we're going to continue talking about that today. Now, um, in the past, whenever I teach graphs, one of the ways that I like to introduce this topic is by having my students go out to the football field to collect data, and then we will come back to the classroom and plot out that data on a position versus time graph to kind of give my students a basic idea of certain trends. So let's look at that right now. So let me just briefly explain what I would do last year with my students and kind of show you guys example an example of some data that came from my last year classes. So typically every year, um, I would get three major volunteers whenever we start our graphing topic. I'll get three main volunteers: a walker, a runner, and someone who walked the field in the opposite direction. Everyone else would basically be off on the sidelines here, lined up every 5 yards with their stopwatches. So they would use the stopwatches on their cell phones to basically obtain time data for the position of my individual volunteers. So, so my walker will start here. If we would call this the zero end of the field, the 0 yard line, and then they will walk all the way here to what is the ideal 100-yard line because the football field is 100 yards. And my runner would do the same. My runner would start here, and they would run from the 0 yard line all the way to the 100-yard line. And then as soon as we got data for those two um, volunteers, then after that, my third volunteer, who is my walker in the opposite direction, basically they would start here at the 100-yard line and they would walk toward the 0 yard line, or what we are calling zero, relative to our reference point. Okay, so this is what we would do. We would get these three major volunteers. We would collect data, and then we would come back to the room and we would put this data in an Excel spreadsheet. Okay? And here is an example from my eighth period class last year. And as you guys can see, we have data for a walker, we have data for a runner, and we have data for someone who walked the field in the opposite direction. And of course, once you take this data and you plot it out on a graph, so for example, let's say you take the walker's data and you put it on a graph, you will get something that looks like this. Okay? And again, we're assuming we're plotting position on the y-axis and we're plotting time along the x-axis. Now, one of the things I said last week, whenever you're plotting out real-world data, you're not going to always get a nice, smooth function. So the purpose of a trend line is to basically give you that smooth function. It's to basically smooth out the human errors here in the data. So we would draw a best fit line through this data to get something that looks like this. And so this line in red here represents the best fit line through my walker's data. And again, it basically allows us to remove those outliers, those error points. So this is what we got for our walker. Here's the best fit line that we got for our runner. And here's the best fit line that we got for our walker in the opposite direction. And of course, and again, these are all position versus time graphs. And I want you guys to notice the runner has a steeper line compared to the walker. And again, we talked about that last week. The steeper the line is on the steeper the slope on a position versus time graph, the greater the object's velocity, because that's what slope indicates. Slope indicates velocity. Okay. So here's our runner, here's our walker, and here's the person who walked in the opposite direction. Notice what's different about them is that, they have a different y-intercept, and of course, their graph appears to be going downhill because that's indicating an object that's moving in the negative direction. Okay, so this is typically how I introduce position versus time graphs with my students. I actually have them collect the data themselves and plot it out so they can get they can get a real world solidification for how these graphs are supposed to look like. And so what I'm just doing now, I'm just showing you guys this, since obviously we're not able to go to the football field. Now, with that said, By the way, those lines that you guys just saw, those graphs represented three objects that were moving at a constant velocity on a position versus time graph. What I want to focus on today, I want to focus on objects that are accelerating, that are either speeding up or slowing down. Anytime we have objects that are accelerating on a position versus time graph, we're going to always see curved lines as opposed to straight lines. Okay, so what I want to do now, I want to go over some important rules with you guys, and then we're just going to look at several examples. So whenever Schoology gets back up, I'm going to upload these rules for interpreting position versus time graphs in Schoology. So most of the Zoom call today, we're going to focus on position versus time graphs. And then toward the end, we're going to get started on velocity versus time graphs. And again, we're mainly focusing on how accelerated motion looks like on these graphs. So let us look over these rules together, and then we're going to just look at several examples. So whenever I give you guys a position versus time graph, there are some important questions you have to ask yourself. The first thing that I would ask myself is if I have a position versus time graph in front of me, and I'm trying to interpret what that position versus time graph is depicting. The first thing I would ask myself, what is the overall trend of the function? Is it going uphill or downhill? And the reason why is because, guys, as a general rule, if your graph appears to be going uphill, that always indicates an object that is moving in the positive direction. If your trend line on your graph appears to be going downhill, that always indicates an object that's moving in the negative direction. Everybody got that? So uphill, positive velocity. Downhill means negative velocity. So this is the first thing you want to notice whenever you're given a position versus time graph. The second thing you want to notice if you're looking at a position versus time graph, you want to ask yourself, does the slope have a curve? And if so, does the slope get flatter with time, or does it get steeper with time? Okay. Guys, as a general rule, if your curve gets flatter with time, that always means your object must be slowing down. As a general rule, if your slope gets steeper with time, that means your object must be speeding up. In other words, the basic trend goes from steep to flat, which means slowing down. And in this case, if we're going from flat to steep, then that must mean speeding up. So these are the important things you need to remember whenever you're looking at a position versus time graph. And in just a moment, let's look at some examples of everything that I just said. Okay. Could someone tell me what's happening here with this motion map? Okay, so guys, for this motion map here, we're moving in the negative direction and we're speeding up. Okay, so those are two main things we notice. Moving in the negative direction and we're speeding up. So that means on my position versus time graph, I better notice two things. I better notice an object that is, I better notice a graph that has a trend that's going downhill and the curve is getting steeper with time. So this is how that looks like on a position versus time graph. This is what you guys should notice. So guys, what I have here a position versus time graph that is speeding up. Specifically, it's speeding up in the negative direction. How do I know that it's moving in the negative direction? Well, guys, what is the basic trend? Remember, as you read your graph from left to right, if you notice, this basic trend is going downhill. So remember, downhill always means our object's moving in the negative direction. Okay. How can we look at this graph and interpret that it represents an object that is speeding up? Well, if you notice, as we read our graph from left to right, the trend gets steeper with time. Here's how you know that. I'm going to draw a trend line at various intervals of time so you guys can get a basic idea of what's happening to the curve. So notice the trend line at 1 second is relatively flat. But if I keep going, if I draw a trend line at 2 seconds, then at 3 seconds, then at 4 seconds, and then at 5 seconds, if you guys notice, the trend line got steeper and steeper and steeper. So it started off relatively flat, and then the curve got steeper. So anytime you're going from flat to steep, that always means an object that is speeding up on a position versus time graph. Now, let us look at some more examples. Let us look at this example here. Okay, so whenever you guys see a motion map like this, you guys should notice two main things. The first thing you should notice is that we're moving in the positive direction. And the second thing you'll notice is that you're speeding up. So that means whenever I look at my position versus time graph, there's two important things that I better recognize on my position versus time graph that is explaining this situation. Since we're moving in the positive direction, I better notice a curve that is going uphill. And since we're speeding up, I better notice a curve that is getting steeper with time. So what does that look like? Okay, so here is an example of a position versus time graph that for the most part depicts an object that is speeding up. Uh, uh, it's speeding up because we're getting steeper with time, and also we're moving in the positive direction. And how we know we're moving in the positive direction? Well, if you notice, as you read your graph from left to right, because time progresses that way, as you read your graph from left to right, if you notice the trend appears to be going uphill. So it's going uphill. So that's how we know we're moving in the positive direction. How do we know that we're speeding up? Remember, if your general trend of your curve goes from flat to steep, that means speeding up. And so we can clearly see here, and I'm gonna draw a trend line at every second to kind of get an idea of what's happening to the curve in the vicinity of that second to see what to see what's happening to the speed as time progresses. So notice the trend line starts off, for the most part, relatively flat. It's nearly horizontal. But as time progresses, it goes from flat to steep. So there's a trend line at 2 seconds, 3 seconds, 4 seconds, and so on. So if you notice, the trend line is going from flat to steep. So because it's getting steeper with time, that means our object must be speeding up. In this case, we're speeding up while moving in the positive direction. Let's keep going. Again, the more examples that we see, the better. what about this motion map here? How would I describe this motion? So if you notice, there are two main things that you guys notice. One, we're moving in the negative direction, and two, we're slowing down. Okay, so if I have to represent this exact same scenario on a position versus time graph, there's two things I better notice. I should notice, one, a graph or a trend line that is going downhill, and I should notice a trend that is getting flatter with time. Okay, because downhill on a position versus time graph indicates an object is moving in the negative direction, and getting flatter with time indicates an object that is slowing down. So the question is, how does this look like on a position versus time graph? So the position versus time graph for this scenario we just watched looks something like this. So, okay, this position versus time graph is depicting an object that is slowing down while moving in the negative direction. How do we know we're moving in the negative direction? Remember, as you read your graph from left to right, so as you read your graph from left to right, you can clearly see that the curve appears to be going downhill. Okay, so that's how you know it's moving in the negative direction. How do you know it's slowing down? Well, the curve appears to be flattening out with time, and we see that because if I draw a trend line at 1 second, you know the line representing the slope of that curve appears to be relatively vertical. So it's 1 second, then draw a trend line at 2 seconds, then 3 seconds, then 4 seconds. As you guys notice, by the time we get over here, we flatten out. So we're going from steep to flat. Okay, so whenever you're going from a trend line that's steep to flat, that always indicates the object is slowing down. So in this case, we're slowing down while moving in the negative direction. Okay, let's keep going. What if I were to give you a motion map that looks like this and ask you to figure out how the position versus time graph depicting this motion would look like? Well, so two things I want you guys to notice. One, we're moving in the positive direction, and two, we're slowing down. So we're slowing down while moving in the positive direction, which means when I have my position versus time graph, I better notice two important things on a position versus time graph. I better see a line or trend that's going uphill, and I better see a curve that is getting flatter with time. So as time progresses, the curve gets flatter and flatter and flatter. And here's how that looks like. Okay, so for an object that is slowing down while moving in the positive direction looks like this on a position versus time graph. So notice as you read your graph, notice how the trend appears to be going uphill. That's how we know we were moving in the positive direction. Now, how do we know we're slowing down? Remember, if the basic trend goes from steep to flat, that means our object is slowing down. And we notice so look at the trend at around 1 second. It's relatively steep, but notice how if you keep going, it gets flatter and flatter and flatter and flatter. Okay, so we go from 1 second all the way to 6 seconds. It starts off, pretty steep here, but then it flattens out here. Um, so we would say this object is clearly slowing down because my trend line flattens out. My trend line basically represents the shape of that curve. By the way, as a little side note, for those of you guys who are in calculus, are you plan on taking calculus in the future? This trend line here in calculus, we call that a tangent line. And what a tangent line is basically a line that touches the curve only at one point. Um, so basically, if I draw a tangent line, for every second, 1 second, 2 seconds, 3 seconds, and so on. Basically, what a tangent line is, the tangent line tells you the slope of the curve at that specific point. That's what a tangent line is. It's the slope of the curve at that point. And again, that's something that you guys talk more about in calculus. I just wanted to throw that out there so that whenever you guys do see that in calculus, you guys can be able to make the connections back to physics. Okay. Any questions on position versus time graphs before we move on to velocity versus time graphs? And again, all of these rules will be in Schoology. Okay, now that we have a basic idea, excuse me, now that we have a basic idea of how accelerated motion looks like on a position versus time graph, let us now discuss the rules of how accelerated motion will look like on a velocity versus time graph. Okay, so let's discuss that. Okay, so whenever I give you guys a velocity versus time graph, you want to ask yourself these important questions. And of course, the basic trends for analyzing velocity time graphs will be different from position versus time graphs because they're different types of graphs. So when looking at a velocity versus time graph, you want to ask yourself these important questions. The first thing you want to ask yourself is, does the function's line appear on the positive side or the negative side? Okay, if the line appears on the top half of the graph, which is the positive side, that means your object is moving in the positive direction. If your line appears on the bottom half of the graph, which is the negative side, that means your object is moving in the negative direction. So everybody got that? Everything above the horizontal axis is a positive velocity, and everything below the horizontal axis is a negative velocity. Okay. So the second thing you want to ask yourself, does the function's trend approach zero with time, or is it going further away from zero with time? Okay. If it's approaching zero with time, that always means our object must be slowing down. If our trend is going further away from zero with time, that means our object must be speeding up. And remember what zero means. Zero represents the x-axis on our velocity versus time graph. In other words, it's the horizontal axis. I'm going to say it again. Approaching zero means slowing down. Going further away from zero means speeding up. Okay, and so now, now that I've gone over these rules, let us just look at some basic examples. Okay. Guys, give me just a second. I'm trying to open up a blank file. Hold on, guys. I need to delete these annotations from the previous class before I show you guys this. Give me just a second. Okay. Okay, so guys, here's how velocity time graphs looks like. Whenever you guys see a velocity versus time graph in this class, you're going to always see two halves. You're going to see a top half, which is positive, and a bottom half, which is negative. So again, everything above the x-axis, above the horizontal axis, is positive, and everything below the horizontal axis is negative. And of course, everything along the horizontal axis is zero. Right? So everything along this line represents zero velocity. Okay, so everybody got that? So you're going to always draw these T-shaped graphs for velocity versus time graphs. Now, suppose I give you a velocity versus time graph that looks like this. So I give you a velocity versus time graph that looks like this, and I ask you, what type of motion is this graph depicting? Well, first of all, someone tell me, what I just drawn, did I draw an object that is moving in the positive direction or an object that's moving in the negative direction? Anyone?
Negative.
No, you're thinking of position versus time graphs. If this was a position versus time graph, that would be an object moving in the negative direction. However, this is a velocity versus time graph. In fact, this object is moving in the positive direction. Here's how I know it's moving in the positive direction. Because I drew my line on the top half. Remember, anything that appears on the top half is moving in the positive direction, and anything that appears on the bottom half is moving in the negative direction. So in other words, if I had taken this same line and I had drew it down here, then that would be a negative velocity because I drew my line on the negative end. But here, this entire line is on the positive end, so that's a positive velocity. Now the question is, are we speeding up or slowing down? Well, hopefully it should be obvious to you that this line here represents an object that is slowing down. Here's how I know that, because remember, as I read my graph from left to right, notice how the line appears to be approaching zero. So if your trend approaches zero with time, in other words, it's getting closer to zero, and eventually here it hits zero, that means the velocity is decreasing. So in other words, it is slowing down. So in this case right here, our object is slowing down while moving in the positive direction. Okay, let's look at some more examples. What if I gave you guys something that looks like this? What if I gave you this for a velocity versus time graph? So I want you guys to notice two things. Here I've drawn an object that's moving in the negative direction, and my object that this line is representing is clearly speeding up. Here's how I know that. I know it's moving in the negative direction because I drew my line on the bottom half, right? Because everything on the bottom half all has negative velocities. And how do I know it's speeding up? Remember, as I read my graph from left to right, the line appears to be going further away from zero. Anything that's going further away from zero is slowing down. And anything that gets closer to, anything that's going further away from zero is speeding up. And anything that's going closer to zero is slowing down. Okay. Can someone tell me if I gave you guys this on a velocity versus time graph, what's happening there? What's going on there, guys? Well, hopefully you guys should see that I drew a line that represents an object that it's moving in the negative direction while also slowing down. So before we were moving in the negative direction and speeding up. Yeah, it's moving in the negative. It's moving in the negative direction and it's slowing down. How do I know it's moving in the negative direction? Well, because I drew it on the bottom half. How do I know it's slowing down? Remember, as I read my graph from left to right, notice how this trend approaches zero with time. And of course, eventually here it hits zero. So as it's approaching zero with time, that must mean an object is slowing down. To be specific, it's slowing down in the negative direction. I'm going to do one more. Now, this time, I want you guys to tell me what's happening here. What if I give you a velocity versus time graph that looks something like this? Someone tell me what's going on there. Anyone?
It's speeding up in a positive direction.
Exactly. It's speeding up in the positive direction. We know it's moving in the positive direction because I drew my line on the top half. The line appears above the horizontal axis. So here it has all positive velocities. So it's moving in the positive direction. And how do I know it's speeding up? Because as I read my graph from left to right, the line appears to be going further away from zero, right? Anything that's going further away from zero is speeding up. Anything that's getting closer to zero is slowing down. Okay? Just something to keep in mind. By the way, I talked about this last week. Could someone tell me what does this mean here on a velocity versus time graph? Let me draw that nearly perfectly straight. Okay, someone tell me, what does this mean on a velocity versus time graph? What's happening here? My object's doing what?
Staying constant.
Yeah, it's moving at a constant velocity. To be specific, it's moving at a constant velocity 2 meters per second. So it's moving at a constant velocity in the positive direction at 2 meters per second. That's how fast it's going. Right? The velocity does not change as time progresses. What does this right here mean? Okay. What does that mean on a velocity versus time graph? So if you guys remember, that means our object is not moving. It's at rest. How do I know it's not moving? It has zero velocity, meaning it is not moving. Okay. So that's pretty much velocity versus time graphs. So I want to close out the day by showing you guys this. Here's a really easy way to remember the rule about velocity versus time graphs that tells us whether or not an object is speeding up or slowing down. Here's something that I want you guys to remember. It's a really easy way to remember that rule. And this is and when I tell my students this, they never forget it. In order to remember that rule on a velocity versus time graph, whether or not something is speeding up or slowing down, is to think of a speedometer. Okay. Guys, if you're driving in your car and you're looking at your speedometer, remember, your speedometer measures your instantaneous velocity at any given point, right? So this helps us make sense of what's happening to our velocity versus time graph. Think about this, guys. If you're in a car and you're driving along and you decide to speed up, in other words, you punch your foot on the gas, you hit the gas real strongly, what happens to your speedometer here? As the faster and faster you go, you notice that the speedometer indicator, it gets further away from zero, right? So the more you speed up, the more your speedometer indicator gets further away from zero. And then someone tell me, what happens the moment you hit your brakes? The moment you hit your brakes, what happens to your speedometer indicator? It does what?
Closer to zero.
It gets closer to zero. Exactly. So remember, speeding up, your speedometer goes further away from zero. slowing down, your speedometer gets closer to 0, and eventually you would come to a stop. So everybody got that? I'm going to say that again. Speeding up, your speedometer goes further away from 0. Slowing down, your speedometer gets closer to 0. So if y'all remember this, you can remember the basic rule on the velocity versus time graph, that whenever you're speeding up, your velocity versus time graph, the trend line should go further away from 0. But whenever you're speeding up, it should go further away from 0. And whenever you're slowing down, the trend line should get closer to 0, just like a speedometer. So hopefully that will help you guys remember that basic rule. Okay, I'm going to stop recording here.